Next topic we're going to cover is called Fourier Transforms. This really belongs in EE206.31 signals and systems. We're going to touch on it right now because once you have superposition, you really have Fourier transforms. Now the problem we've been looking at is if I have a circuit with a sinusoidal input, I use phasor analysis. If the input has multiple inputs, I use superposition and treat it as n separate problems, each with a separate sinusoidal input. If you have an input which is not a sine wave, then what you could do is what we did on the last lecture, change the problem so that the input is a sine wave. That's what we do in EE320 electronics. I treat that as a DC term and a sine wave, then analyze the two parts separately. That doesn't give you exactly the right answer, but it's close. If you want to get more accurate, you can simulate it, or you can use Fourier transforms. That's this topic. So what we're going to do is change the problem so that the input is a sum of a whole bunch of sine waves. So what the Fourier transform says, if my input is periodic in time t, that's what this says. X of t is x of t plus capital T. Every capital T seconds, the period, the signal repeats, hence it's periodic. If that's the case, then I can express x of t in terms of a DC term and a bunch of sines and cosines, where each of these is a harmonic or multiple of the fundamental. Now in English, what that means is here I've got a function x of t, which is periodic. Here I've got a bunch of sine waves. They're equal. Equal is a very powerful signal, a very powerful symbol. What it means is the two are exactly the same. Not approximately, but exactly the same. Going right to left, what this says, if I have a bunch of sine waves that are periodic in time t, if I add them up, the answer is periodic in time t. Well, that's kind of obvious, so that's like a big duh. The interesting part is going left to right. If I go left to right, if my signal is periodic in time t, then I can decompose it into a bunch of sine waves. That's the power of the Fourier transform. Any signal that's periodic, be it a heartbeat, a voice, a piano, if the signal is periodic, it's composed of a bunch of sine waves. The importance is, once it's expressed in terms of sine waves, I can use superposition to solve the problem of finding the output. The first problem, however, is how to find the Fourier coefficients. How to find a sub 0, a sub n, b sub n. There's a couple ways to do that. The analytic solution is you do a bunch of integrations. Stay tuned for EE343 for that. You can also do a numerical solution. That's using MATLAB. That's what we'll do in this class. To find each term, what you want to do is find the a0, a sub n, b sub n separately. The answer is that a sub 0 is just the average of x of t. A sub 1 is the average of x of t hit with cosine omega naught t. B sub 1 is the average of x of t with sine 2 omega naught t times 2. Now the proof of that comes from all sine waves being orthogonal. For the a0 term, suppose I have x of t, and from the Fourier transform, this is what it's equal to. To pull off the a0 term, just take the average of x. The average of a0 is just a0. The average of a cosine is 0, so that goes away. The average of a sine wave is 0. This goes away. Taking the average of x just gives you a0. Hence, a0 is the mean of x. To find term a1, take x of t, that's what we had before. Now take twice the average of x hit with cosine omega naught t, where n is 1. If I substitute, I'll have a0 times cosine. That average is 0. I'll have sine times cosine. All sine waves are orthogonal. The average of sine times cosine is also 0. I'll have cosine times cosine. The average of that is also 0, except in the case when n equals 0, in which case I'll get cosine squared. The average of cosine squared is a half. A half times 2 is 1. So what I'm left with is a whole bunch of zeros, except the term that I want. That'll give me a half times 2, or a1. Hence, the average of x of t hit with cosine of omega naught t times 2 gives you the first term. The same thing happens with b sub 1, a sub 2, b sub 2, and so on and so on. That's how you find the Fourier coefficients. There is a shortcut. Time is not a universal constant. I can do a change in variable and change the period to be anything I want. A period which is very convenient is 2 pi. The reason I like 2 pi to be the period is because the fundamental frequency is 2 pi over the period, or in this case becomes 1. In that special case where the period is 2 pi, the Fourier transform is just a0, all the cosine terms are just cosine nt, sine terms are sine nt, and it makes the math a little bit easier. We'll be doing that in MATLAB, changing it so the period is 2 pi. To give an example what the Fourier transform looks like, we'll look at a couple periodic signals and show you what the Fourier transform does. Suppose, for example, I've got x of t is 3 cosine 5t. Find the Fourier transform. This is actually a trick question. The Fourier transform just says express x of t in terms of sine waves. X of t is already in the form of sine waves, hence the Fourier transform is just x of t, so we're already there. If I take x of t, the Fourier series, add up all the terms out to a couple terms, and compare to the actual x of t, they're exactly the same. 3 cosine 5t is 3 cosine 5t. So Fourier transform of a sine wave is easy, it's just a sine wave. Harder one. Suppose x of t is a square wave. It goes from 5 volts to 0 volts to 5 volts to 0 volts. And the fundamental frequency is 5. To find the Fourier coefficients, what I can do is change the problem so the period is 2 pi. These numbers will be exactly the same. They don't depend upon the period. When I'm done, however, the answer will be a DC term, the first harmonic, second harmonic, in this case the third harmonic. There's no fourth harmonic, fifth harmonic. These will all be multiples of the fundamental, 5. If you do the Fourier transform using MATLAB, I'll get the constants of 2.5 at DC, 3.18 at 5 radians per second, the first harmonic, minus 1.05 at the third harmonic, 0.64 at the fifth harmonic, and so on. Add all these up, I get the red waveform. This is the Fourier series approximation to a square wave taken out to the fifth harmonic. If I go out to infinity, these will match exactly. Another example. Triangle wave. If I have a triangle wave, the blue line, and I take the Fourier series approximation to it, going out to the fifth harmonic, here the period is 2 seconds. So the fundamental frequency is 2 pi over t, which is pi. Here's the first harmonic, third harmonic, fifth harmonic. Go through MATLAB, find the Fourier transform of a triangle wave. What I'll get is this. It's 0.5 at DC, minus 0.405 at the first harmonic, minus 0.045 at the third harmonic, minus 0.016 at the fifth harmonic, and so on. To show that these are actually the same, if I plot x of t versus the Fourier series approximation now to the fifth harmonic, I get the red term for the Fourier series, blue term for the actual function. As I get closer, or as I add more and more terms, the two get closer and closer. Fourth example, half-rectified sine wave. If my function is periodic in 2 pi, this is where 2 pi is kind of nice, then I've got the first harmonic, second harmonic, fourth harmonic. The numbers work out a little bit nicer if we make the period 2 pi. So x of t is a half-rectified sine wave. Do the Fourier series approximation using MATLAB. Find the different terms, the DC term, first harmonic, second harmonic, third harmonic, add them all up, and get the red line. What this shows is that if I have a function which is periodic and not made of sine waves, the blue line, using Fourier transform, I can turn it into a whole bunch of sine waves. The advantage of doing this is, unlike the previous lecture where I came up with an approximation that kept the flavor of the problem, there is no approximation here. The Fourier transform is exact. If I carry this out to infinity, the answer I get using the Fourier series will be exactly the same as the answer I get using the function. The advantage being is with the Fourier series, I now have just a phasor problem. This I can solve. Likewise, any function or any input that's periodic I can solve using Fourier transforms. That's the power of superposition. That's the power of Fourier transforms. I can solve a circuit for any input that's periodic. So in summary, if the waveform is periodic in time t, I can express it in terms of sine waves, that's Fourier transform, and I can now solve the circuit.